Good day, I'm Dr. T and welcome to my office. So today I would like to jump in and go beyond our star system and talk about stars and our galaxy and galaxies far away. So to do so, I first want to jump in and talk about measuring distance because we're way too far for a tape measure, and if we're going to map things out, we're going to have to measure things out. Now, there's roughly 3 ways of measuring distance on astronomical scales that I want to talk about. These are kind of the big 3. The first is what we call parallax. This is triangles in space, but we can actually see this quite clearly on a more terrestrial version because most of us use this on a very regular basis. So take some random object like the audio recorder I've got here, or a pencil, your finger, whatever you want. Hold it a little bit away from your face. Now I'm going to say close left eye, right eye. It doesn't matter which eye is which, just one or the other. So if you close your left eye, you're looking at things, and one, you notice you've kind of lost depth perception. Individuals who don't have full function in both eyes generally lose a lot of depth perception because they're only looking at the world through one eye. As such, you'll notice everything got a lot less deep, a lot less rich. Now, you're going to close your right eye and open your left, and it gets kind of blinked back and forth a bit. What you will notice is that the thing you were holding up close to your face was moving a lot. It was jumping around. That's because my left eye, or your left eye, is looking at it at one angle, and then when we switch, the right eye is looking at it at a different angle. We can use those angles as part of a triangle. By knowing those 2 angles and the distance between our 2 eyes, we can then calculate how far away it is. This is how most vertebrates do a lot of our depth perception. And as such, why individuals with impaired vision in one eye lose a lot of their ability to do depth perception. Not all of it, because we've got a couple other ways of doing things, but definitely some of it. If you looked at that, it jumped around quite a bit. Do it again real quick, but pay attention not to the thing you're holding, but the things far away. For me, that would be my messy kitchen and the dining room beyond. They don't move as much. Because if you think about it, they're triangles. They've got a triangle going on, but their angles aren't going to be as far because the part you're looking at is much farther away. The further away is, the sides of the triangle will be closer to parallel, and the difference in the angles is going to be fairly minimal. So if you know the angles and you know the distance apart, you've got yourself everything you need to know for your triangle, and you can figure out where the point is. This is kind of the whole deal with triangulation. We're just going to expand it by observing the star twice, 6 months apart. If we look at it 6 months apart, we know where we were 6 months ago. We know where we are because, we're doing laps around our star, and we know how far away we were. We've got the base of the triangle. We have the angles from each measurement. That gets us 2 of our 3 angles. That allows us to calculate the third. And if we know all 3 angles and a side of a triangle, you know the other 2 sides as well as how far away you are from the center of one of the sides, where the star is. Yay! We've sorted out everything we want. Now, there's a downside here. The distances have to be relatively, once again, on astronomy level, relative is a big term here, but they have to be relatively close. So we're not looking at distant galaxies doing this. We want stars that are somewhat close to us. Otherwise, the difference in the angles aren't going to be much of anything. In fact, we measure the angles against the more distant stars. And the stars we see are all not that far away. They're all within our home galaxy, more or less. So, as we're looking at them, our kind of local stars, our neighbors, we can measure distance to them pretty regularly by looking at angles. By the way, this is where the term parsec comes as a description of the change in angle, thus making a parsec a length unit, which creates some awkwardness for a fan base of a particular 1970s era sci-fi film. But we won't go there. Okay, I was going to skip this step, but I do want to jump into what an actual parsec is. So the idea on the parsec is that a star 1 parsec away from us would be observed between the Earth and then where the Sun is, so a triangle with a base of 1 astronomical unit, it would observe a 1 arcsecond difference between a line from the Earth to it and between the Sun and it. This distance is going to be just a smidge over 3¼ light years. Should probably say what a light year is. Light has a fixed speed limit. It's, in a vacuum, 3 × 10⁸ meters per second, which is ridiculously fast under most scales, but once we're moving into astronomical distances, it's actually meaningfully slow. A light year is the distance light takes to travel in 1 year. As such, something that's a parsec away, if you were to send a photon towards it, wouldn't get that photon for roughly 3¼ years, just a smidgen over. Parallax only works if you're relatively close, otherwise the angles are just the same. So how do we go a little bit further out? You've got 2 options, and I'll go with the newer of the 2, and that is redshift. So this one's developed by Erwin Hubble, the guy the telescope's named after. And what he realized is if you look at the spectrum of a star, and by the way, I need to clarify, he is not working alone. This is a collaborative effort. He kind of sends it the last mile. He's the one things get named after. The constant that will be used is named after him. It's the Hubble constant. Okay, so you've got the spectrum from a star. You take the light, you run it through a prism or diffraction gradient. Diffraction gradient's little slits, creates constructive and destructive interference. You spread out light into its respective colors. Now, what you'll notice is there's gaps in it. This is called a dark line spectrum. If you remember all the way back when I did videos on chemistry, you've got atoms, they've got electrons going around them. If you put energy into an atom, you can take an electron from the ground state and kick it up to an excited state and then down to the ground state. When it goes up, it's going to absorb energy. When it goes down, it's going to emit energy. If you put energy in and you're going to get light out, because when it goes down, it's going to give energy off quite often in the form of light, you get a bright line spectrum, because you get a bunch of distinct lines with those exact jumps that it makes. Likewise, if you put light in, say a pure full spectrum light like you would get from a black body radiator, something that's really hot like the core of a star, then the energy can be absorbed, and then when it's released it kind of goes in weird directions and maybe doesn't all make it into the form of photons. It can go into jiggling the atoms and whatnot. This means that in the bright line spectrum, you saw these energy jumps for the molecules as bright lines on a dark background. In the dark line spectrum, you see a bright background with dark lines where the black body light got absorbed in those narrow ranges. They're the same spectrum, though. And so if you know one, you know the other, and they act as a chemical fingerprint. What Hubble realizes is that those fingerprints were in the wrong spot. They were all shifted towards the red side. This is called redshift. It's the Doppler effect. It is quite literally the Doppler effect. If they are redshifted, that means it's becoming a longer wavelength. It's going away from you. Everything in the universe is going away from us. The farther away things are, the faster they're going away from us. The explanation is that the universe is expanding. Just as if you blow up a balloon, every point on the surface of the balloon gets further away. The universe is expanding. The further away 2 points are, if you're blowing up that balloon, the faster they're going to expand away from each other. The same goes for the universe. Thus, by knowing how fast things are moving away from you, you can backtrack and figure out how far away they are using the Hubble constant, which is part of the equation for it. Now, this is great, but you would need to calibrate this. That means you need to know how far away things are. You can do so for local stuff, but not far away things. So we need a third method, one that works at least frequently. It doesn't have to always work. Because we don't have to calibrate for everything. We can use redshift for most things, but we got to calibrate the redshift, and it needs to work further away than does parallax. So what we are going to use are standard candles. Not the things you light, but stars. See, we can compare the intensity of a star that we observe to the intensity of the star at the star. Light, as it gets farther away from the source, gets dimmer, and it follows the equation. The observed intensity, or I, equals the strength of the source divided by 4 pi r squared. Basically, the equation is saying that the amount of light you observed is proportional to how strong the light is and what fraction of the sphere of light coming out of it that your eyeballs are able to take up. The closer you are to the light source, the greater percentage of that sphere you're able to take in with your eyeball, and therefore the brighter it is. So a star could be dim because it's a dim star, or it could be dim because it's far away. If we know the initial brightness of the star, then we can figure out how far away it is. Okay, how do we know the initial brightness of the star? Well, that's where the standard candles come from. There's actually quite a few of these things. Hubble worked on what are known as Cepheid variables. In this case, you've got a star that is going to change brightness on this regular kind of pulsating approach. Not the same as a pulsar, by the way. That is a spinning star. We'll get to those a little bit later on. Okay, so you've got a star that changes brightness, and the regularity of how often it goes bright and kind of blinks at you tells you a function of its intensity. Alternatively, you could use type 1a supernovas. This is a case where you've got a binary star, so two stars that are actually orbiting each other. These are actually incredibly common. And one star explodes, it gets old, it poofs up, and its gases then kind of get dissipated. Then the next star starts to do the same, and then the core remnant of the first star that went kaput has stopped doing fusion. It sucks up the gases from the second star, and it gets enough mass that it restarts. Because this triggers at roughly the same mass every time, type 1a supernova are reliably the same brightness. Now these things are some pretty big booms. These are one you would not want anywhere near you, but especially in distant galaxies, so very far away, they're bright enough to make a notice, and if you know how bright a type 1a supernova is, well, you can compare the strength of the brightness to how it looks to your apparent brightness. By doing that, you can sort out the distances. And this works quite far away. Once again, these supernovas are really bright, so you can see them in distant galaxies. So this gives you a couple ways of doing this. You can, if it's close, use triangles. Most things you can use the redshift, so how their light has been distorted. And if you are able to work out what the absolute magnitude is, how bright the star is at the star, and you know the apparent magnitude, which is much easier, just how bright it is at the telescope, you can compare those and you can work out how far away it is. Okay, so we can work out how far away different stars are, and that allows us to start doing some mapping. So let's look at a map of our home. Okay, last time I talked about the solar system. We got our solar system, and you start going out. You got the inner planets, the outer planets, Oort cloud, and then we're going to start seeing our local stars. Now, we're kind of a field star. We're just kind of floating, more or less, not by ourselves, but we don't have any close, intimate companion stars. Some stars, however, are part of what's known as a star cluster. And to explain a star cluster, I kind of need to go through a rough description of the life cycle of a star. Stars are going to start out as nebula. Nebula are large clouds of gas and dust in space. When originally discovered, they were observed from the ground. Most stars look like points of light. Compared to the distance involved, they're very small. As such, they can only be resolved as a single point of light. But nebula are large clouds of gas illuminated by stars in and around them. As such, they actually look kind of fuzzy. They're not a single point of light. Relative to how far away they are, they can actually be somewhat good size, and so we can see these fuzzy blobs in space. Now, these fuzzy blobs in space can have imperfections in their gravity. They're not necessarily all uniform, and so gravity starts pulling together. And as you get little clumps of gravity, it pulls things closer into each other, and you get a positive feedback loop. More gravity, more clumping, more gravity, more clumping, more gravity, more clumping, more gravity, more clumping. You get the idea. The gas and dust starts clumping together. While it is, if there's any spin at all, which there will be, angular momentum takes that tiny little bit of spin, and as you clump it in from dozens of astronomical units away and clump it into a nice little clump, it's going to be spinning like crazy. Now, as they clump in, all of a sudden the amount of gravity is getting pretty high, and it's trying to crush itself. And this mass of gas and dust is crushing in on itself so hard that the atoms start smashing into each other, and you get fusion. Now at this point, you get a burst of energy, and you're going to go through this kind of irregular cycle, a boom-bust. The fusion tries to blow it up. Keep in mind, this is the exact same concept as at the end of a hydrogen bomb. You take a bunch of energy to squish it. A hydrogen bomb uses an atomic bomb to do this. In this case, we're going to use gravity, and it's going to cause it to blow up. But there's enough gravity, it pulls back in together again, and it blows up. It pulls in, and it blows up, and it pulls in, and it blows up, and you get this kind of cycle. It's going to level out. It's going to reach an equilibrium at a point, and that you get yourself a star. And in this process, it's probably all spinning in a disk, and that disk might break off and start spinning it and clumping together into some planets. And congratulations, you have yourself a solar system of some flavor. Now, in a star cluster, quite often all the stars kind of formed around the same time. The idea is potentially a supernova detonated relatively nearby, created a pressure wave that then proceeded to squish the gas together and kicked off the whole process, potentially. So, in a star cluster, you got a bunch of stars of similar age, created presumably from the same nebula. Now, let's talk about life cycle of stars. As you go through that chaotic sequence, you're going to kind of reach equilibrium, and you got that stable adulthood of your star. We call this a main sequence star. The more gas and dust you have in there, the greater the pressures, the more fusion, and the more intense the energy is going to be on the inside of that star. So big stars are going to burn brighter. Once again, by burn, I mean engage in nuclear fusion, so metaphorically burn. There's no fire there. Now, as they're burning hydrogen into helium, they're doing so at quite the clip. So a big star is going to be very hot. If you remember anything from light bulbs, the color of the light bulb is described by the temperature. Now, it's not actually the temperature of a light bulb for an LED light. They hopefully don't get too awful hot. Otherwise, things are not going right, and it'll probably release the magic smoke. But that temperature is if there was a piece of metal or a piece of something, it does not matter what it is, was that temperature, this is the color it would glow. And that's how the older incandescent light bulbs work. A little hot wire. Well, the hotter the star is, the higher the color temperature because it's just that hot. So big stars are going to be generally very blue. A little bit smaller, you're going to get a little bit more white, then yellow, and then the smaller ones are going to be more of red into like a deep red star. Because the small ones aren't doing that much fission because they don't have that much gravity to happen in. Now, if you're a big star, you've got lots of fuel, lots of mass, but you're burning through it very quickly. Those will generally have relatively short lifespans. Where if you're a small star, you don't have much fuel, but you're burning through it very slowly. You're just sipping your fuel. As such, they'll have much, much longer lifespans. So generally, the brightness is inversely correlated with the lifespan of your star. Now, eventually, the fuel is going to run low. Well, the hydrogen fuel is going to run low, but helium will still fuse. As you're going down the periodic table, you can gain energy through fusion all the way down to iron. Now, past iron, you won't gain any energy from fusion. Fusion is actually endothermic past iron. It takes energy to put in there. And this is all due to E equals mc squared. The mass of a proton is slightly more than the mass of a proton in a helium nucleus. This is, by the way, it's known as mass defect. And the mass of a proton gets smaller and smaller and smaller all the way down to iron, in which case it starts getting bigger and bigger and bigger. So you can gain energy by fusing other elements, not just hydrogen. But this requires a new equilibrium to be established. So as you transition from burning hydrogen to helium and then your other elements, you're establishing new equilibriums. Generally speaking, in this process, you're going to slough off a lot of the outer layers. So the star is going to start expanding and you're going to get a red giant. It's very big. It can be fairly bright, but it's big because it's kind of falling apart kind of scenario. Now, depending on the size of the star, depends on what could happen. If you're a relatively small star, like our sun's kind of a medium-sized star, eventually the gas giant is going to kind of poof out. The outer layers are going to turn back into a nebula, what we call planetary nebula. It looks kind of like a planet through the telescope. It's not, but it kind of looks like one. And then the core becomes a white dwarf, basically the cooling off center. However, if your star is a bit bigger, it gets a little bit more dramatic. In that process, it can actually explode, creating a nova. The remnants now can be a couple of different things. The outer layer is... Now, the remnants can be a couple of different things. If it's large enough, the outer layer, once again, is going to turn into a nebula that will go back into being a recycled planetary nebula. But depending on how big it is, the core could be something like a neutron star or a black hole. Now, neutron stars are basically where you pack the matter in so tightly that the Pauli exclusion principle, the thing keeping atoms apart, is more like the Pauli exclusion force, and it doesn't succeed. It's one giant atom, kind of, not really. Interesting feature, though, this thing is going to be spinning fast, incredibly dense, intense spinning, and it's going to have electric charges going on, so it's going to have a very intense magnetic field. And it may very well be sending radio waves out the axes of that, and it's probably going to be wobbling. This is the pulsar. A pulsar is a radio pulse on a fairly frequent basis, and this is due to your neutron star blinking, and that beam of radio waves, as it's wobbling around, happens to point at the Earth on a very regular basis. It's going to pulse. Of course, if your star was even bigger, it may very well leave a black hole. A black hole is where there's so much mass, it kind of breaks physics, and the density gets so high that the amount of gravity around it is able to suck light in, and light can't escape the gravity, thus it's a black hole. Physics doesn't really work very well inside the black hole. We understand things quite well, but inside the black hole, we got some good ideas, but physics does kind of break in that point. But either way, the outer layers are going to turn back into a planetary nebula, and you cycle over again. By the way, as you're doing the whole exploding bit, you do generally make heavier nucleuses. So remember, you lose energy in the process of, say, going from iron to gold, but if you smack them hard enough because you're exploding, then, oh well, you went from iron to gold. So that does happen. Okay, so you've got your nebula. It forms stars. They can become a star cluster. Now, as we zoom out, once again, gravity continues on very large scales. So these nebula all have gravity. They're attracting everything else. And quite often, stars and nebulas and other things are going to start kind of going around a center of mass. Because remember, big cloud, clump in, is going to spin. And this clump of stars and nebulas and other stuff is known as a galaxy. They come in quite a few different flavors of galaxy. I'm not going to go into that. But you can now have this kind of arrangement of stars, etc. It's thought there's a giant black hole in the center of most galaxies. I will defer that to the experts on how certain that is for that particular topic. Now, like everything else, galaxies attract each other. So galaxies can have a local group of galaxies. And then you can get larger organizations of galaxies. Eventually you reach the known universe. The known universe is basically as far away as we can see. Anything farther away, the light has gotten too far to go and has not reached us and probably never will, because the universe is expanding. At a certain point, you're moving too far away, too fast for the light to actually reach us. Beyond that, don't know. In the topic of further reading, I would like to suggest the 1977 film, The Powers of 10. In the documentary, this is one of those classic documentaries, you know, definitely National Archive grade. The film is it's a short film, looks at a couple picnicking at in a park, and then zooms away. And every 10 seconds, it zooms away an order of magnitude further. So at t equals 0 seconds, they're 1 meter by 1 meter field of view, so you see the blanket. And then at 10 seconds, it's 10 meters, you see the park. At 20 seconds, it's 100 meters, so you're seeing part of the city. In the 1977 version, this is Chicago. There's a 1996 remake that the city is Vienna. And there is a 2022 remake where the city is someplace in Cyprus. All very good choices. CGP Grey did a very similar video, but powers of 2, in which case the city is London because CGP Grey. These are a great viewing. I do strongly encourage everyone should check these out. I like the 1977 version the best, but it is nearly half a century old, and a lot has been learned in the intervening half a century. So I'm probably going to recommend the BBC version that was done in 2122. Okay, so with that said, have a wonderful day, and I will see you, hopefully, in future videos.